Okay, example 2 is the exact same kind of problem. The difference between example 1 and 2 is the function itself a little bit more unpleasant. We have 5 times 1/2 to the x power. Again, we have our power expression in our problem, making this an exponential function. The only variable in the whole problem is x, which is right there, which is the power of 1/2. So again, if that's the situation, I'm going to pick -2, -1, 0, 1, and 2. Again, nothing magical about those numbers. There's just, those numbers tend to be, they're going to give me the more reasonable answers that I want. I'm evaluating 5 times 1/2 to the x power, so as I'm typing these in my calculator, I'm going to practice it. F of x equals 5 times 1/2 to the x power. Right, so a couple options. Option 1 is 1/2 is the same as 0.5. I can either go with 0.5 to the x power, or I can go with 1/2 to the x power. If I want 1/2 to the x power, let's say I'm going 1/2 to the third power. So if I do 1/2 to the 1/2 to the third power. Try again. 1/2 to the third power equals that, parentheses 1/2. It actually works. Suppose it was 2/3. 2/3 to the 2 power to the third power, and then parentheses 2 divided by 3 to the third power. See how they're different answers? Your calculator needs to know it's being raised to the power. It's only going to raise one thing to the power unless you tell it to do more than one thing. So I want this whole 1/2 being raised to the power. I'm going to put parentheses around it. Even though for a half it worked both ways, it doesn't work the same for all fractions. So let's get a habit here of doing this correctly. So for me, if I'm doing this, I'm going to do 5 times parentheses 1/2 end parentheses caret -2. Hit enter, is 20. Now this calculator, most calculators, if you press up, it brings up the last thing you typed in, right? This calculator happens to, you have to hit the second enter to make that happen, and you just change the -2 to -1, over type it. So this is 10. Change that to a 0. That's 5. Make this a 1. That's 2.5. And then make this a 2. Right. Now there's my points. Now you'll notice before I plot the points that this time it doesn't look like it's getting close to anything, right? It's kind of getting smaller. Maybe it's getting close to 1. I'm not quite certain, right? But the negative numbers create big answers, the positive numbers getting smaller answers. So it's getting smaller as it goes this way. It's got to flatten out to something as I go this way. I'm not sure exactly what it flattens out to. The way you find out that number, if you can't figure it out just by looking at it, just pick a big number. And when I say big number, when we're dealing with power, something in the 20 to 30 range is probably big enough. So let's say 20. That's 0.00004. Zero, so one more 0. 0.00004. There we go. That's pretty close to 0, right? Okay. If I try a bigger number, let's say the 30th power. That's 0.000000004. Seems like it's getting close to 0, right? So my asymptote here is going to be at y equals 0 again. So again, if I plot my asymptote, horizontal line where it happens, I'm going to identify what it is. Y equals 0. I'm going to plot my points. Now these points got rather large on me. My graph only goes up 1, 2, 3, 4, 5, 6, 7, 8, 9. It goes up to 10, right? This point doesn't fit on there if I'm using a 1-to-1 scale. So one option is to use a 2 scale on the y-axis to get up to 20. Option 2 is let's just not plot that point. You pick a point and it made a number that's unpleasant to graph, toss it. Right? If the rest of the points are good, that's good. If not, we can find more points. So -1, 10 is here. 0, 5, 1, 2, 3, 4, 5 is here. 1 comma 2.5 is here. When you get decimals, just approximate, so 1, 2, and a half, right? 1.25 is 1 1/4, so there you go. And it's kind of going up, flattening out this way. Now here's a situation where maybe I want to pick a couple extra points here just to get a little bit more clarity about what the graph looks like as I go this way. So maybe if I extend this down a little bit, maybe I'm going to pick 3, 4, and 5. Again, they're getting smaller, so it's going to be on the picture. It's not going to pass 0. So if I just come over here and pick the 3rd power and the 4th power, that's 0.625. And the 4th power, that's 0.3125. And the 5th power, that's 0.15625. Couple decimal places really is enough. 0.63, 0.65 are pretty much the same spot I'm estimating, right? So 0.63 would be about here. 0.31 would be about here. 0.16 would be about here. Anytime you're trying to graph and you need more clarity about what the graph looks like, grab a few more points. Your calculator will evaluate all the stuff for you. If I want to get another point coming this way, you know, obviously this is the top of the graph. If I go any further this way, it's going to go above. But there's a negative half and there's a positive half. I can get a couple points in there also if I want to. And not required, but if you want to, you can definitely grab them. So if I go negative 0.5 and positive 0.5, again, my calculator is evaluating all this stuff, so it's not hard to do. Negative 0.5 is 7.07. Positive 0.5 is 3.54. So negative a half, 1, 2, 3, 4, 5, 6, 7, and a little bit, so just above 7. And then positive 0.5 is about 3.5, so 1, 2, 3, and about a half. Yeah, those points just help fill in the picture, give me a better view of what it looks like. If you don't need those, don't worry about getting them, but if you, again, need more information, you pick more X's, get more Y's, get more answers. Plot every answer. And then notice, again, it's flattening out one side, it's going up to infinity the other side, so the graph is going to just connect those dots in a smooth curve. And it's not going to hit the asymptote, so it's going to level out as it goes that way. So there's our graph. The domain is anything we're allowed to put into this function. The graph goes forever to the right and forever to the left. So the domain is a set of all real numbers. The range, about f of x, is where the graph lives vertically. The bottom of the graph is 0. It doesn't get 0, but it gets above 0 and everything bigger. So f of x must be greater than 0, not greater than or equal to. So be careful that's greater than. What's the intercept? 0, 5, right? That's the only point where it crosses the axis. So it crosses the y-axis at 0, 5, right here. It does not cross the x-axis. If it did, I'd point those out also. But 0 comma number is a y-intercept. Number comma 0 is an x-intercept. This doesn't hit 0, so there's no x-intercept. And behavior as x approaches, as x goes towards negative infinity, what happens to the graph? As it goes this way, it gets infinitely bigger, right? Y is infinitely bigger. As x is approaching positive infinity, what's happening to the graph? Y gets closer to 0. Your end behavior is going to look like that in exponential functions. One way is going to get closer to some number. The other way is going to get either infinitely bigger if it's going towards positive infinity, or infinitely smaller if it's going towards negative infinity. Some of these graphs. So, what's that? That's a positive sign. Positive infinity. My pen slipped on me a little bit. That was all right. So, as x approaches one of the infinities to the other infinity, one side is going to be closer to a number, the other side is going to be either infinitely bigger going towards positive infinity or infinitely smaller going towards negative infinity. The other one's always getting closer to whatever the asymptote value is. The asymptote is y equals 0, it gets closer to 0. The asymptote happens at y equals 6, it's going to get closer to 6. All right, whatever that value is what it's going to get close to. So end behavior is pretty straightforward once the graph is drawn. So that's how you do what we're doing right now. The homework assignment involves this type of problem. Make sure you have graph paper. Use graph paper for these problems. Don't try and freehand graphs on your paper.